In this video, I'm going to explain Dijkstra's algorithm. It's an algorithm to help us find the minimum path between 2 points in a network. So that is the path that has the shortest distance for a weighted network between 2 points. First of all, a bit of kind of why would we do this? So, for some of the networks we'll be looking at, you might think that, it's pretty easy to just look at the network and find the shortest path through what we might call inspection, just kind of trying different things or trial and error. But if you think about more complicated networks, like say how Google Maps might find you a way between 2 points very far apart, it becomes harder. And so having an algorithm to get a computer to do it for you is very helpful. It was made by this guy, Edgar Djikstra. And he was a Dutch guy, so it is pronounced Djikstra, if you want to get that right. And yeah, the process we follow, I've got on the next slide. And if you would like, you could screenshot that process and put that in your band reference. That way you'd have it there to refer to, but I'm just going to show you how it works through a few examples. So if you'd like to pause the video, screenshot that, put in your band reference, you're welcome to. But yeah, let me show you how it works with some examples. So here, what we're asking to do, we're trying to go from A to B. So, we're starting here and we're ending here. The way Dijkstra's algorithm works is you can kind of think of it as just kind of exploring the network through different ways of, how much distance is it between each of our points here. So with this network, we're starting at A here and that node is labeled 1. And so if we're saying, okay, well, how far is it to 2? When we've come from node 1, it's a distance of 7. And then we could do up here at node 6, right? So coming from node 1, so we just write that first of where is the last node we've come from? It's distance of 14. And to node 3, so coming from 1, it was a distance of 9. Now, if you think about going, say, here and then here, that would overall be a distance of 19. Oh, wait, no, sorry, excuse me. It would be 17. 7 plus 10 makes 17. Now that is a number bigger than 9, so we don't bother, updating this point here. We've already looked at that. We've already looked at that. Now, if we came, say, this way, it would overall be 16, so we're not going to care about that. And so, yeah, so far we've got our shortest distance here. Now, if we go this way, so from node 2, it would be 22 if we came this way. From node 3, though, it would be 9 plus 11, so it would be 20. So we go that way, we can get rid of that and say, okay, from node 3, actually, it's overall 20 from our starting point. Now we go this way along here. So from node 4, it's 26. Alternatively, we could come from here. And so from node 6, it's going to be a shorter distance of 23. And then if we want to get the path, so our shortest distance is 23, and the path itself, we just kind of count back. So, so node 5 is our endpoint. Before that, we were on node 6. Before that, we were at node 1. Okay, and that is our shortest path. So yeah, it gets a little bit messy, but got that there. I'm going to do another example, just a bit of a harder one. So this one, yeah, it's this one. Perhaps we can see a bit more why we would do this algorithm of that. It's less immediately obvious, what the quickest way to get from A to G is. So here we got our start, here we got our end. So I just do that process. Okay, so from A, it is a distance 3 here. From A, it's a distance of 12 here. From A to this one, distance of 8. So we've kind of got rid of each of those. If we then think about, okay, well, actually, if I went this way, so via this one, right, do this and this. So from B, we could get there in 7. And then if we went this way, it would be 15, so we don't care about that. We could go, okay, down here, it's going to be, so from D, 17. Overall, we're at 7 here, plus 9 makes 16. So actually from C, we got 16 down there. Going that way. Then if we go up here, say, we could go, okay, so from C, we're overall at, so 7 plus 1 is 8. Oh, they're actually going this way. What, it's 3 plus 2. So coming from B, it is only 5. Okay, getting to G here, we could go down this way and it'd be 19. So coming from E, 19 overall. If we went this way, it would also be 19 actually. So also from F, 19. See if there's a better way. If we came this way, so 7 plus 12, oh, also 19. Huh. That is interesting. I wonder if I made a mistake here. I've ignored something. Because, it seems like we've got multiple paths that all have the minimum value of 19. Let's look at our next slide. Yeah, apparently there's a different way. Oh, I obviously didn't explore everywhere. Let's go back and think about what have I missed. So up here we got to 5. So to get to C, let's have a different color here. But if we go this way, we can get to C in just 6. Very tricky. So we got to really make sure we're updating all of these labels. So coming from E, we're at 6. And then we can go down here, and coming from C, we're only at 9 rather than 12. Going along here, so 9 plus 5 gives 14. So we can get to F by 14. Sorry, get to F from D, 14. Plus 3 is 17. So all of these guys can go. And we've got coming from F, 17. And that is our minimum path. And so what? We came our last spot. So we ended up at G. Before that, we're at F. Before that, we were at D. Before that, we're at C, and then E, and then B, and then A. So yeah, we obviously have to be very careful about making sure all of these labels are the actual minimum path from the starting point, or otherwise you'll make a mistake like I have. But yeah, so once you've updated all those labels to be accurate, you can see that the shortest path is 17, and it's this kind of pretty hidden path that you probably wouldn't see unless you did that whole algorithm. That is it for this video. Thanks for watching.